Start by pausing this video and answering the questions to the quick quiz. Pause the video to check and make corrections to your answers. This lesson is on Hooke's law and elastic potential energy. By the end of this lesson, you will be able to describe the effect of unbalanced and balanced forces. You're going to state the difference between elastic and inelastic deformation. You'll be able to understand and use Hooke's law to solve problems. You're going to link your prior knowledge of energy transfers to this new knowledge of springs. And you're going to use the elastic potential energy equation to solve problems. So, we're going to start by discussing the forces acting on these four different objects. We've got a car that's moving forwards, a skydiver that's falling towards Earth, a mass on the end of a chain that's attached to a crane, and a boat that's not moving but is floating on water. Pause this video and have a go at naming the forces acting on these objects. So let's start with the car. The first force I'm going to label is weight, which acts from the centre of mass, which is roughly the centre of this car, and it goes downwards towards the centre of the Earth. Next force is the normal contact reaction force. This is the surface pushing back onto the car where the car is pushing on the surface. I've got two arrows here that show the normal contact reaction force. There should be four because there are 4 points of contact from a car on the surface of the Earth. Next is a driving force, because I said the car was moving, and the driving force creates air resistance and friction from the tyres on the surface of the road. So the skydiver also has weight acting from the centre of mass down towards the Earth, and has air resistance acting in the opposite direction. The mass on the end of the chain has weight acting down from the centre of mass straight down, and tension acting in the opposite direction. That's the force of the chain pulling back. The boat also has weight pulling down, and instead of the normal contact reaction force, there is upthrust, which is the opposite force to the weight. Let's have a look at a specific example of an unbalanced force. So here we have a motorbike which will have weight acting down from the centre of mass straight down, and it will have normal contact reaction force. Now you'll notice that the arrows, there are two of them because there are 2 points of contact from the motorbike to the ground, and each of them is half the size of the weight arrow. This tells me that in this direction, up and down, there is no resultant force. The motorbike is not moving up or down. Let's say this motorbike is moving, so there is a driving force, and also air resistance and friction. Now, if I take away the image, it's clearer to see that in the left and right direction, the driving force is much bigger. This means that the forces are unbalanced. There is a resultant force. This tells me that there is a change in velocity, so the motorbike is accelerating. Let's have a look at the skydiver. So here we've got weight acting from the centre of mass down and air resistance acting up. Now, as you can see, the arrows are not the same size. The weight is much bigger than the air resistance, and therefore the resultant force is not zero. This means that there is a change in velocity, and it means that the skydiver is accelerating. Now, let's have a look at some balanced forces. Balanced forces cause deformation, not movement. Deformation means a change in shape. So, for example, if we have two forces pulling on an object in opposite directions, like this, then the object will stretch, like this. If we have two forces pushing the object from opposite directions, like this, then the object will compress like this. Now, balanced forces can also cause a bend in an object. If forces are applied like this, then the object will bend like this. Now, a note to see is that the two arrows on top are half the size of the arrow on the bottom. This tells us that the forces are still balanced. There is a resultant force of 0 still. If an object undergoes elastic deformation, that means it will return to its original shape after the forces have been removed. So for example, two forces pull on this object, it stretches, the forces are removed, and it goes back to its original length. I can show you another example where two forces are pushing on an object, it compresses, but then the forces are removed and it goes back to its original shape. Inelastic deformation is where an object is either stretched or compressed and it does not return to its original shape after the forces have been removed. So let's have a look. Two forces pulling on this object, it stretches, the forces are removed, but it doesn't go back to its original shape. Another example where forces are pushing on the object, it compresses, the forces are removed, but it doesn't go back to its original shape. That's inelastic deformation. Pause this video and have a go at the questions. Pause this video and have a go at the questions. Look at the forces acting on a spring. So the first one is the weight of the mass acting downwards from roughly the centre of the mass. And we then have tension, which is the force of the spring pulling back on the masses, and that acts in the opposite direction. Now these two arrows are the same size, and therefore there is no resultant force, and so the mass is not moving. Let's have a look at stretching a spring. Now we stretch a spring by increasing the force downwards, or the weight acting on that spring. As you can see, the larger the mass on the end of the spring, the greater the weight, and therefore the spring will stretch further. This also means that the tension in the spring is larger. And we see the same thing for compressing. As we add a bigger mass onto the end of a spring, it will compress more because there is a greater force of weight. Let's have a look at three different springs when we add the same mass and therefore the same force onto the end of each of them. As you can see, each of them extended by different amounts. And this is due to how springy the spring is. On the left, you can see a thick, stiff spring. This one did not extend very much when the mass was added. In the middle, you can see quite a thin, loose spring. This one extended by the most when the mass was added. The stiffness or springiness of a spring is called the spring constant, and it describes how easy or difficult it is to make the spring stretch or compress. When we talk about the stretching or compressing of a spring, we are interested in the difference between the original length and the final length. Springs with a high spring constant might look like this. They take a lot of force to stretch or compress. You might find these types of springs in car suspension. Medium spring constant springs might be the springs that you find around outside of a trampoline, or the springs you find in a mattress. These require slightly less force to extend or compress them. Springs that require very little force to stretch or compress have very low spring constants. They might be the springs that you find in a clicky pen. Let's have a look at some graphs that show the force applied to a spring and the amount the spring extends by. Okay, so if we have a look at these axes, we've got force measured in newtons on the y-axis and extension measured in meters on the x-axis. This line, the straight line, shows us that as force increases, extension increases at the same rate. The line goes through the origin at this point here, and therefore we can say that force is directly proportional to extension. The next graph, we've got the same axes, so force measured in newtons and extension measured in meters. This graph also shows a straight line, which tells us that as force increases, the extension increases at the same rate. This line also goes through the origin, and so we say that force is directly proportional to extension. The interesting thing about this graph is that it shows us a spring with a much higher spring constant, a spring that is more stiff. I know that because as force is applied, the spring extends much less than it did over here. So this graph down here has the same axes, force in newtons and extension in meters. And this line is straight and therefore tells me that as force increases, extension increases at the same rate. However, this one does not go through the origin, and therefore we say that force is proportional to extension, not directly proportional. And finally, same axes, force in newtons and extension in meters. This graph shows that as force increases, the extension also increases, but not at the same rate. And so we say that in this case, force is not proportional to extension. Robert Hooke was an English scientist in the 1600s, and he did some work on stretching and compressing springs, and so he has a law named after him. Hooke's law states that the force applied to a spring is directly proportional to the extension of that spring. Pause this video and say Hooke's law 3 times. So this graph shows force applied to a spring and the extension of that spring. This data shows Hooke's law. It shows force and extension are directly proportional because the data shows a straight line that goes through the origin. We can work out the force applied to a spring based on how stiff the spring is and how far it extends. Hooke's law says that the force is equal to spring constant times the extension, where force is measured in newtons, spring constant is measured in newtons per metre, and extension is measured in meters. Pause this video and write down the equation with the quantities and units. Pause this video to check and make corrections to your answers. We're now going to practice using this equation by answering questions from the Hooke's law and elastic potential energy worksheet. I'm going to do a few examples and then you'll pause the video and have a go at more questions yourself. So, question 1 says that the extension E is 0.2 metres, and it says that the spring constant K is 20 newtons per metre, and we are trying to find the force F, so F equals question mark. The next thing we do is write the equation at the top of the next side, that the force is equal to the spring constant times extension. Force in this case is equal to 20 times 0.2, and on a calculator I will do 20 times 0.2, which is 4 newtons. Question 2 says that the extension of a spring is 0.6 metres, so E is 0.6 metres, and the spring constant K is 15 newtons per metre. And again we want to find the force. So force is equal to spring constant times extension. Force in this case is 15 times 0.6. And again on my calculator, 15 times 0.6 is 9 newtons. Now I'd like you to pause this video and complete questions in section 1. So question 9 says that the spring was 0.7 metres and it was stretched to 0.9 metres. And so to find the extension, we do 0.9 metres, take away 0.7 metres. That gives me an extension of 0.2 metres. The spring constant is 25 newtons per metre. And we're looking to find the force. So I write the equation, force is equal to spring constant times extension. So force is equal to 25 times 0.2. On my calculator, 25 times 0.2, and that's equal to 5 newtons. Question 11 wants us to find the extension when the spring constant of a spring is 20 newtons per metre and the force applied is 4 newtons. The next step is exactly the same. I'm going to write the equation at the top of the next side. Force is equal to spring constant times extension. Then put in the numbers I know. So 4 is equal to 20 times extension. Now to find the extension, we need to divide both sides by 20. Since 20 divided by 20 is 1, we can ignore that and just in the calculator do 4 divided by 20. And in decimal form that is 0.2. So the extension is 0.2 metres. Question 12. We need to find the extension when the spring constant of a spring is 45 newtons per metre and the force applied is 5 newtons. So exactly the same way to start, write out the equation in the same way, F equals KE, and we put numbers in, so 5 is equal to 45 times E. Now we divide both sides by 45 to get E on its own, and since 45 divided by 45 is 1, we can ignore that, and in our calculator do 5 divided by 45, and in a decimal form that's 0.1 recurring, and so we can round that to 0.1 metres. Question 14 says that a spring extends by 0.2 metres and we need to find the spring constant K when a force of 4.4 newtons is applied. So we write the equation, as always, in the same form, F equals KE. The force in this case is 4.4 newtons, and so we can write 4.4 equals K times 0.2. Now to get K on its own, we divide both sides by 0.2, and since 0.2 divided by 0.2 is 1, we can ignore that, and on our calculators we'll do 4.4 divided by 0.2, and that gives us an answer of 22. So the spring constant K is 22 newtons per metre. Question 15 tells us that the extension of a spring is 1.5 metres. We want to find the spring constant K when a force of 28 newtons is applied. So we write the equation, force is equal to spring constant times extension. 28 is equal to spring constant times 1.5. To get K on its own, we divide both sides by 1.5. And since 1.5 divided by 1.5 is 1, we can ignore that, and in our calculators do 28 divided by 1.5, which gives us a decimal answer of 18.6 recurring, which rounds to 18.7. And so the spring constant is 18.7 newtons per metre. When a force causes an object to move a certain distance, we say work has been done or energy has been transferred. Look at stretching. So, as the mass was added to the end of the spring, the gravitational potential energy of the mass decreased. This is because the height to the surface decreased. Now, since this energy has decreased, and we know from the conservation of energy law that energy can't just be destroyed, the energy must have been transferred somewhere. This energy has been transferred to the elastic potential energy of the spring. So as the gravitational potential energy decreases, the elastic potential energy increases. The amount of elastic potential energy gained or lost by a spring depends on two things. Firstly, depends on the spring constant, how springy or stiff the spring is. Elastic potential energy also depends on how far the spring has extended or compressed. This leads us to an equation for elastic potential energy. Elastic potential energy is equal to half times the spring constant times extension squared. Please write down the equation and the constants, where energy is measured in joules, spring constant is measured in newtons per metre, and extension is measured in metres. We're now going to practice using this equation by answering questions from the Hooke's law and elastic potential energy worksheet. I'm going to do a few examples, and then you'll pause the video and have a go at more questions yourself. Question 21 says that there is a spring with a spring constant of 20 newtons per metre. It says that the extension is 1 metre, and we've been asked to find the elastic potential energy. So I draw a line and write the equation. Elastic potential energy, EE, is equal to half times the spring constant times extension squared, or KE squared. Elastic potential energy is equal to half times 20 times 1 squared. Elastic potential energy is equal to, I'm going to use my calculator, and it's important to only square the extension, so you'll notice that the square is only on the 1. and that gives me an elastic potential energy of 10 joules. Question 22 says that there's a spring with a spring constant of 35 newtons per metre and an extension of 0.8 metres. And we've been asked to find the elastic potential energy. So elastic potential energy is equal to half k E squared. The elastic potential energy is equal to half times 35 times 0.8 squared. So we only square the 0.8. And in decimal form, that gives me an elastic potential energy of 11.2 joules. Okay, let's have a look at question 31. So this says that there's an elastic potential energy of 200 joules. The spring has extended by 0.8 metres. And we've been asked to find the spring constant. So write out the equation. Elastic potential energy is equal to half ke squared. We're going to put in the numbers we know. So 200 joules is equal to half times k times 0.8 squared. Now the first thing I'm going to do is get rid of the half. And I do that by doing 200 divided by 0.5. So that gives me 400, which is equal to k times 0.8 squared. So I'm going to save myself some time and do the 0.8 squared now, which gives me 0.64. Now we have a simple equation that we can solve by dividing by 0.64 on both sides. So 0.64 divided by 0.64 is 1, so we can ignore that and do 400 divided by 0.64, which gives me a spring constant of 625 newtons per metre. Question 32. We've been given an elastic potential energy of 650 joules, an extension of 0.5 metres, and we've been asked to find the spring constant. So write out the equation as always. Elastic potential energy is half times k times extension squared. In this case, 650 is equal to half times k times 0.5 squared. So I'm going to get rid of the half by dividing by 0.5, which gives me 1,300. And that's going to be equal to k times 0.5 squared, which is 0.25. Now I'm going to solve by dividing both sides by 0.25, and since 0.25 divided by 0.25 is 1, we can ignore it, and we just need to do 1,300 divided by 0.25. And that gives me a spring constant of 5,200 newtons per metre. Question 5 asks us to use Hooke's law and elastic potential energy within one question. So let's have a look at question 40. Part A says there's a force of 40 newtons applied to a spring, and that causes an extension of 0.5 metres, and we've been asked to find the spring constant. So the equation we're using is Hooke's law, F equals KE. 40 newtons is equal to K, the spring constant, times 0.5. So I'm going to divide both sides by 0.5, and since 0.5 divided by 0.5 is 1, we can ignore that, and then our calculators do 40 divided by 0.5. That gives me a spring constant of 80 newtons per metre. Part B asks us to calculate the elastic potential energy stored in this spring. Now the extension is 0.5 metres, and the spring constant we worked out in part A to be 80 newtons per metre. The equation for elastic potential energy is E is equal to half KE squared. So elastic energy is equal to half times 80 times 0.5 squared. And when I type this into my calculator, I make sure that I only square the extension, which is 0.5 metres. And that gives me an elastic potential energy of 10 joules. Part C says if we apply a bigger force, 50 newtons, to the same spring, with a spring constant of 80 newtons per metre, how much is the extension? So we use Hooke's law that says that force is equal to spring constant times extension. 50 newtons is equal to 80 times extension. Divide both sides by 80, remembering that 80 divided by 80 is 1, so we can ignore it. And we type in 50 divided by 80 into our calculator. And as a decimal, that rounds to 0.63 metres. Spend about half an hour now working through some more questions, and if you have any problems, then send me an email.